In this video, without going too complicated, I'm going to show you how to integrate and why it is that that works. But just before we start, a quick reminder about differentiation. So differentiating polynomials. If we have a simple polynomial, some constant multiplied by x to the power of n, then differentiating it with respect to x gives us n a x to the n minus 1. In other words, we have multiplied by our power and then decremented the power. Now, we looked at that in previous videos and we looked at why this is. We went through the derivation of this equation and we've looked at some cases where we use this equation. It's also worth noticing that when you have an expression, some function y of x, which has two terms, then you can just differentiate each of the terms separately and write those down, and that works fine. And the most important thing to remember now is that integration is just the opposite of differentiation. Integration is anti-differentiation. So if we have a graph of some function displacement versus time, and we've seen graphs like that before in earlier videos, we know that if we differentiate this, we get a graph of velocity versus time. And if we differentiate that, we get a graph of acceleration versus time. Well, integration is doing the opposite process. If we have a graph of acceleration versus time and we integrate it, then we get a graph of velocity versus time. And if we integrate that, then we get a graph of displacement versus time. Now, we remember that in the physics context for this. We don't have to get into bogged down details of drawing trapeziums and making those slithers even smaller and adding them up and all sorts of things you'll see when mathematicians teach integration. And they teach it really well, of course they do. But this is far simpler to just remember that rule. So, integration, what is it doing? It's giving you a function that allows you to calculate the area. And the area it allows you to calculate is between the line of the function that you're integrating and the x-axis. In the previous video, we looked at certain cases in physics where it might be useful to do this, to find the area between a line and the x-axis. Our acceleration here is expressed in the form y equals mx plus c, where on the y-axis we have our acceleration, and on our x-axis we have time. And remember, we defined acceleration as a rate of change of velocity. So if we want a function of the velocity as a function of time, if we want that function, then we have to integrate this equation. So first, let's multiply through this by dt. Remember, dt is a small, an infinitesimally small interval of time on the x-axis. And dv is an infinitesimally small interval of velocity. Well, if I want to find out what the velocity is after a certain amount of time, let's use t as the example, capital T. Then what I'm doing is I'm integrating from 0 to that time. And the notation we use is 0 on the bottom and a t on the top. This symbol, this strange s, we're using for sum. We're summing all those little bits of velocity, starting from 0 seconds all the way up to t seconds, to find out what the final velocity is. Well, whatever we do to one side, we have to do to the other. So we also have this sign here, which indicates a sum from 0 to t on the right-hand side. Well, this term here on the left-hand side, adding up all the bits of velocity, you're just left with what the velocity is at the time t. And that's because we started from 0. We'll look at cases where you don't start from 0 towards the end of this video. But that just leaves this strange thing on the right. How do I integrate a with respect to t? And I have the function for a here on the left. Well, the way that I think is easiest to remember this is to start with what differentiation was. And if you remember integration is the opposite, then it's straightforward. With differentiation, first of all, we multiplied by the power. N here went here. Then we decremented the power. That means we reduced it by 1. Now that's what we did when we differentiated. So when we integrate, we're going to do the opposite, in the opposite order. The last thing we did was decrement the power, So instead we're going to increment the power. That means increase it by 1. And the first thing we did was multiply by the power. So we can do the opposite. We can divide by the power. Well, it's the new power. It's the power that's been incremented. So our expression for a as a function of time was this. And we are trying to decide what the integral a dt is equal to. Well, notice that this has got two parts to it. This plus this. So we can handle those two parts separately. I substitute for a, this entire equation, and then I've split it into the two different parts. This is the mt part, and this is the c part. This expression, we decided, was equal to the velocity at some time. That's what that expression was equal to. So let's start now integrating these terms on the right. With this term, the power is 1. This is the same thing as m times t to the power of 1. So I'm going to increment the power. That means I'm going to increase the power by 1, and it becomes a 2. And then I'm going to divide by this new power. That's where that half comes from. So we end up with this expression at the bottom here. The integral mt dt is equal to half mt squared. Now the term on the right, c is a constant. It was a constant in this equation. It was the y-intercept. It's still a constant. And constants can be taken outside because there's no change in them. They can be taken outside the integral. So if you sum up all those little time steps, you just end up with the total time. And there we have it. That equation on the bottom is the integral of a as a function of t dt. So now I've got an equation for the velocity at a time t. Assuming the velocity was initially 0, I can just plug in now what the time is, and I can find out what the velocity is. And it came from this expression of the acceleration. That's very, very powerful. But you notice I said, assuming that the velocity was initially 0. It might not be. So remember that if I differentiate any constant, it's going to equal 0. Because differentiating something is finding a rate of change of one variable with respect to another. If a variable is constant, it's not changing, so the derivative is just 0. Well, that means we can do the opposite, of course. I mean, I can multiply through by dt and then do the integration sign, and that means that if I integrate d of some constant, it's the same as integrating 0 dt. And if you look at integrating 0 dt, your instinct might be, well, that's just 0. But it's not. It can't be, because we're adding up small intervals of some constant, whatever that means. You're just left with the constant. So this thing here is equal to some constant. Now it could be 0, but it might not be 0. So if you have a look at this equation that we had before, acceleration equals mt plus c, that was in the form y equals mx plus c, I could have added plus 0 on the end. I could have done. The equation's still exactly the same. So here was the integration we did last time, but this time I'm going to have plus this integration of 0 on the end. And so here's what we derived last time, but now plus some constant at the end. Now, very often we call that constant c, the constant of integration. But as I've already used c because I'm using the line of best fit as my function of a, I didn't want too many c's floating around, so I've just left it named as constant. Or alternatively, we could use a capital K. So what is that constant? What does it represent? Well, have a look at what happens when time t equals 0. When time t equals 0, that is 0, that is 0, and we're just left with that constant. So in other words, it's what the velocity is when the time is 0. It's the initial velocity in this case. And of course, we could now move on and integrate that function to find an expression for the displacement at a time t. So remember that the first derivative of displacement with respect to time is the velocity function of time. Therefore, if I multiply through by dt and then integrate, I get this. This term here on the left is just going to be s as a function of time. And this term here on the right, well, I've got to integrate this expression here. And I can do it in 3 separate stages because these 3 terms are added. And because there's also plus 0 on the end here, then I have this extra term on the end here as well. So here we have the integral of half mt squared dt. Well, I'm going to first of all increment the power so it becomes a 3 and then divide by that power. So a half divided by 3 becomes a 1/6. With this term here, we have ct. That means it's a power of 1. So first of all, I increment the power so it becomes 2, and then I divide by that new power, so I get a half. That's where the half ct squared comes from. This term here, we've got v0. Well, that's multiplied. v0's a constant. I can take that outside the integral. So that's multiplied by the integral dt, which is just t. And once again, we've got this integral here, which is equal to a constant. But we don't know what that constant is. If I worked backwards and just differentiated that constant, it would vanish. So that's how that constant came about. But we don't know what it is. But you can see in this case that the constant is what the displacement would equal when t would equal 0. In other words, it's the initial displacement. So I could replace that with S0, some initial displacement. And there we have it, an equation for the displacement. And I started with an expression telling me what the acceleration was doing. And I could work in reverse. I could have started with a displacement expression and worked back to acceleration. And remember, what we're doing is modeling. So it might be that we think our acceleration is going to reduce over time for some reason due to air resistance. And we plot a graph and we think, I think that's what the acceleration does. And then we conjure up some expression that matches those data points on our graph. Then we can integrate twice to find what the displacement is at any time. Very, very powerful. Let's just go back a step and have a look at the velocity expression we had. And here I've got a k as the constant. Let's go through and replace those with v0. And I've shown you how to find the significance of that constant. Just set the variable to equal 0 and see what the constant means. In the case where the variable is time, it's the initial value. But, it could be different depending on your physical situation. So here was exactly the same expression we're working with. I haven't changed anything, but now we're saying, well, what's the change in velocity from time t1 to time t2? Well, our expression for velocity, just our general expression, was this. So we can plug in t2 here and t1 here. Those are the two expressions where I've just substituted for those two particular values of time. The difference in velocity is going to be the final velocity. Velocity is a function of t2 minus the initial velocity. Velocity is a function of t1. Well, here is velocity as a function of t2, and here is velocity as a function of t1. And just be careful of those signs, because I'm subtracting this velocity. All of these are minuses. Now what you can see is this v0 cancels out. And if we just simplify this expression, we can factor out the half m and the c, and we're left with this. So the key thing here to remember is that when you have definite limits on your integration from some number to another, those constants cancel. And you represent those limits by using the numbers or letters here and here on your integration. And so that's it. Very, very straightforward approach to integration by knowing what differentiation is and working in reverse. And you can do the same thing for trig functions as well. If you know how to differentiate from one trig function to get another, you just work in reverse. And it works for exponentials as well. Exactly the same idea, just work in reverse. Now in the next video, we're going to look at a few more physics examples of where you might find yourself integrating.